Hello, I am Laura Gillam, the Marketing Manager here at Physics World. I would like to welcome you to this webinar, Tunable Lasers in Quantum Research, Novel Lasers for Novel Colour Centres. This webinar is brought to you by HÜBNER Photonics, a manufacturer of high-performance lasers. We have three speakers from HÜBNER Photonics with you today. The first is Jarro Sperling, the Global Sales Manager for HÜBNER Photonics, who has a background in laser spectroscopy. Following Jarro would be Corbinian Hens, a product manager for HÜBNER Photonics. Corbinian joined the company in 2015, specializing in terahertz spectroscopy and tunable laser systems. You will also hear from Nick Vassem, Regional Sales Manager and Application Specialist for HÜBNER Photonics, who has been with the company since 2014. Our speakers welcome your questions, so please send them in at any time during the webinar using the question facility on your screen. We will try to answer as many questions as possible at the end of the presentation. We also have a handout available, which you can download from the right-hand panel. Now, I'll hand the webinar over to Jarro.
Yes, hello. So welcome everyone. Happy you can join today. I'd like to start with a quite general observation I came across recently. So as most of you will be aware, there is a big buzz going on regarding quantum technology and quantum computing. So end of last year, you will know probably that Google or the Google team published a paper, a Nature paper about supremacy of their quantum computer over conventional devices. And this really created a big buzz, not only in the community, but also in everyday newspapers like New York Times or the Washington Post. What is remarkable when you look at the number of citations, so this has been published end of October, so not much more than half a year from now, and I checked yesterday, it has 136 citations. So it's being cited like every 36 hours. Yeah, there is a big buzz going on. While we are not the manufacturer of quantum computers, the purpose of today is to show you where we fit in this global picture and what advantages we can offer. So we will talk about tunable lasers in quantum research, or to be more precise, novel tunable lasers for novel color centers. We will start with a very general introduction, then focus on design, challenges, and performance of our novel tunable laser sources. And before wrapping up, we also wanted to give you some real-world application examples. So let me start with the impossible, which is summarizing quantum research on one slide. So what you see here essentially is a list of buzzwords. But simply speaking, quantum technology is about creation, control, and detection of single quantum objects. Many people expect what they call a second quantum revolution. So these type of devices to enter applications like computing, cryptography, sensing, and many others. There might be mixed views on how soon these devices will enter everyday life, but I think we will all agree that sooner or later we will all get affected by these kind of devices. The device architectures essentially rely on, simply speaking, on manipulable quantum systems, two-level quantum systems in the simple case, that are typically manipulated with coherent lights, or continuous wave coherent lights, which will be continuous wave laser lights. Also a crucial role play so-called single photon emitters, which are quantum systems that process exactly one photon per excitation event. and color centers belong to this class of systems. While there is a variety of single photon emitters in discussion, a lot of research is put into so-called solid state single photon emitters, which have the advantage that they can be processed in the solid state, and hopefully can also, or the desirable can be also operated at room temperature. So to name a few, there is the so-called nitrogen vacancy color center in diamonds, which is arguably the most frequently or the most studied color center in photonics research. What you see on the left is the diamond, or a set of the diamond lattice, and nitrogen vacancy refers to the fact that the nitrogen occupies carbon side, and on the opposite side is a vacancy, is a carbon missing. So this is the NV center. Quite recently, I think not longer than 2 years ago, other color centers have been discovered, which go by the name of group 4 color centers in diamonds, which are slightly different. So there is a group 4 element, like silicon, germanium, tin or lead, occupying a vacancy in diamonds. There are not only diamond photonics materials, there are also other candidates. Just to name one, this would be hexagonal boron nitride, which is two-dimensional material, like graphene. So it has the ultimate layer of miniaturization, at least in one dimension, and so it would have quite desirable properties. And also these defects in hexagonal boron nitride offer a lot of potential advantages. We will get back later in a bit more detail on experiments on these color centers, but I would like to start with some generic features or some common spectral properties. So basically, I would say that quantum research is the search, might be called the search for the perfect two-level system. In the best case, it will be separated from the environment, or it will not feel the environment at all. In that case, the absorption and emission spectrum of a two-level system would be identical, so just a single peak in the spectrum. In the terminology of solid state physics, this goes by the name zero phonon line. So this would be the behavior without any environment. Now, the reality is that the quantum systems, they feel their environment, sometimes more, sometimes less. And this leads to the appearance of so-called phonon sidebands in the absorption and the emission spectrum. So simply speaking, in absorption, there are phonon overtones excited, and the opposite process happens in emission. In total, you get this characteristic spectral shapes in absorption and emission. On top of that, when you look at an ensemble of single photon emitters, then every emitter will feel a slightly different environment, which will in total further broaden the spectrum by inhomogeneous broadening. My point is, when you think about experiments on these type of systems, we deal with really different kind of spectral features. So there are zero phonon lines. When you look at them at low temperatures, they can be very narrow, less than 10 picometers. when you look at ensembles of inhomogeneously broadened systems, we look at the region of over 100 nanometers. So there are 4 to 5 orders of magnitude in the spectral width. Just to give you an example how this looks in the real world, so these are the photoluminescence spectra of the group 4 color centers. So without going into details, but you see this goes over a range of more than 200 nanometers. So for experiments or to characterize such samples, what are the requirements for the light source or for the laser light source? Well, ideally, one would have tunability across the whole spectral range, which is the visible spectral range in our case, a sufficiently narrow line width to characterize narrow feature like zero phonon lines, and suitable wavelength tuning mechanisms that are suitable to either characterize the very narrow features or an inhomogeneously broadened ensemble. Now, so this would be the requirement. So let's maybe have a short look what's out there in terms of common laser solutions. The next slide, this one looks pretty messy, but let me explain. So this is an overview or a whole list of commercial laser lines I took from Wikipedia actually. So this goes from the ultraviolet to the mid-infrared. On top you see non-tunable laser line. On the bottom part you see the tuning ranges of certain laser gain media. So this looks, at first sight, this looks like pretty messy and pretty, looks like everything is covered. However, when you do a close-up in the visible range and try to look for solutions that would give you tunability across the range, say 500 to 700 or 650 nanometers, then in fact there is not so much left. So here we see there are dye lasers are mentioned here. When you look a bit closer, so also dye lasers for each individual dye have only a limited tuning range. So my point is there are not as many solutions or not so many convenient solutions as you might think. The reason for that, I'm sorry, I skipped. I'm sorry for that. So the reason for that, when we recall the laser principle, which I guess most of you will know, which relies on population inversion in a medium, which is created by a pump source, and essentially laser emission relies on stimulated emission in a laser gain medium. But my point is here to recall that to generate a certain laser wavelength, you need these levels to be present. So you need a suitable set of electronic levels. And actually, this is one of the, if you wish, limitations of laser technology or the wavelength coverage, is the search for a suitable gain medium with suitable energy levels. What we want to present you here is an alternative approach, which is optical parametric conversion in devices called optical parametric oscillators. This is a process which relies essentially on splitting an incoming photon into other photons or photons of other energies. This is typically the incoming photon will be split in a signal and idler. So that's a 3-wave mixing process. The process is subject of conservation of energy and momentum. But it's important to mention that it's a parametric process, which means there is only a virtual level involved, which gives you flexibility. So there is no need to be on any resonance here. So at least in theory, you could use any pump frequency, and also by manipulating this medium, it is possible to split the ratio of signal and idler. Corbinian will get back in more detail into that. But for a wrap up of the introduction, I would say, well, on the one hand, we have recent advances in quantum research and nanophotonics that that call for continuous wave laser light sources that offer wide tunability across the visible range on the one hand. On the other hand, there is the potential of OPOs, which derives from their wavelength versatility, as in principle they are not limited by a particular gain medium. So while this sounds quite good on paper, let's say, there are some reasons why the OPO concept has demonstrated relatively recently. Well, the concept itself has been demonstrated soon after the laser concept. However, the commercial or practicable devices have emerged only recently only. And I hand over to Corbinian to explain this in a bit more detail and to look in more detail on design challenges and performance that can be achieved.
Yeah, thank you, Jaroslav. As mentioned before, I will give an overview about the OPO process, some design considerations, and also concepts to build a widely tunable CW OPO covering the visible wavelength range with sufficiently narrow line width, and it should be also suitable in its tuning mechanisms for quantum research. And on the next few slides, I try to give you an overview how we can achieve this. So we have already seen this principle of the OPO process, and basically an input photon, a pump photon, shown here with the green arrow, is converted by a nonlinear optical process into two lower frequency photons, the so-called signal and idler photon. And this process underlies the laws of conservation of photon energy and conservation of photon momentum. Well, how does that look in realization? Typically, a pump source, a coherent pump source, which is a pump laser, is directed to a nonlinear medium for that OPO process. And then the third main component that is needed is a resonator. We show here a bow tie resonator, but basically it could be also another type of resonator. It's just quite compact and therefore also commonly used. That's why I show this picture here. So what does, maybe we step back to the conservation of photon energy. What does this conservation of photon energy restriction or constraint imply for this process? So, well, the pump photon energy or the pump photon frequency is the sum of the resulting frequencies of the signal and the idler photon. And that seems to be quite obvious. That means that the pump laser frequency is always higher than any signal and idler frequency that can be produced in such a process. And well, that explains the left part of that equation. Just by convention, the one with the higher frequency of signal and idler is called signal. But if you just express the same equation from above, so the photon energy conservation in terms of wavelengths, you also see that signal and idler wavelengths are always dependent. So to give you an example, if you pump a nonlinear medium with, for example, a green laser at 532 nanometers, and let's say by whatever magic I explain later, 900 nanometer is the output wavelength of the signal, then you can calculate that the idler wavelength needs to be something like 1300 nanometers. And by splitting between the signal and the idler, can be controlled by changing, for example, the temperature of the nonlinear medium, or I wrote already here, a nonlinear crystal is typically used, or you can also change the orientation by tweaking this crystal. You can change, for example, with the same pump frequency, so 532 nanometer pump, to a signal output of 1040 nanometers, but then the idler is, per definition, you can calculate that around 1090 nanometers. Just having that in mind, that these two are dependent, still this constraint of photon energy is rather straightforward to be understood. It's a bit more tricky if we talk about the photon momentum. Photon momentum and photon energy need to be satisfied. The conservation law needs to be satisfied for both simultaneously to run the OPO process efficiently. And this photon momentum conservation is also often called a phase matching condition, which means that the interacting photons in the nonlinear medium have a certain phase relation which needs to be maintained within that crystal to make that process efficient. Unfortunately, the refractive index of most materials is quite frequency dependent, and that means if we have different frequencies in one crystal, definitely there, or let's say the likelihood for a phase mismatch within such a crystal within that process is very high, and a phase mismatch would lead to destructive interference of the generated photons, limiting the number of photons, worst case even, canceling them out, all of them, and definitely limiting also the efficiency of that process. So how to overcome this issue of a phase mismatch? Well, there is different phase matching technologies, and if you talk about fixed frequency lasers, that's a well-known problem, usually using birefringent materials, angle tilting of a crystal and so on. There are different phase matching options, but we need something which is suitable for a tunable laser, so not for fixed frequency, and therefore we need something more fancy, and luckily there is a solution for that, which is called the quasi-phase matching technique, using periodically poled crystals. Essentially, that means these crystals, these nonlinear media, are periodically structured in a way that they change periodically their nonlinear optical properties, compensating the phase mismatch, and this can be done very efficiently, so you can build crystals of several centimeters length and therefore provide enough interaction length inside crystal for making an OPO process really efficient. So here we talked about the crystal, I talked about the pump laser, and maybe you remember the third thingy we need is a kind of a resonator around that whole thingy. Well, I also mentioned already that bow tie cavities are quite compact and often used. Just for sake of completeness, other cavities could be used as well. Anyway, this is a design which you will find quite often also in commercialized solutions of OPOs. But a very basic design consideration is the question how to make the resonator resonant, only resonant on one of both output waves. So for example, resonant on the signal, or what we show on the right side, doubly resonant OPO design. So we have a cavity which is resonant on the signal as well as on the idler wave. Both designs have advantages and disadvantages, and I show that here with the plus and minus indicated for each of the cavities. Let's maybe start on the bottom right side. So the advantage, the main advantage I would say of doubly resonant OPO is that the pump threshold can be lower, typically in the range of tens of milliwatts that are required, or maybe even hundreds of milliwatts, but definitely lower compared to the singly resonant OPO, which is typically having, here on the left side, you see there's a minus enhanced pump threshold. Typically for singly resonant OPOs, the pump threshold is at least in the 500 milliwatt up to more than 1 watt range. On the other hand, if we go back to the doubly resonant OPO, there's also a disadvantage of that doubly resonant one because of that additional constraint that we have on the cavity. I mean, having a cavity resonant for a CW laser means that the length of the cavity is the multiple integer of that wavelength which is circulating. And if we have two different wavelengths, the wavelength pair of signal and idler, which are dependent, as I mentioned before, circulating around, and both of them need to be resonant, well, that means we have a additional restriction on the length of cavity that are possible, and that leads to a non-monotonous wavelength selectivity. So it's much easier by tuning, for example, the singly resonant design on the left side. If you temperature tune, change therefore temperature tune the nonlinear medium, therefore change the wavelength. You can just change the length of the cavity for the resonant signal, and you're done. So to make a continuously tunable laser in the visible with narrow line width, that was what we are aiming for. The singly resonant OPO design is what we want to look into a bit more detail. So I said already narrow line width. Maybe one thing, those of you who know about laser resonators would probably directly see that this resonator on the left-hand side is definitely everything else than narrow line width or single mode. It would be multi-moding and support many, many, many modes. So how do we get to a single mode operation and narrow line width laser from this? So here we use concepts that are well known from other types of lasers. We use kind of frequency filters, so-called ettalons, which have a periodic filtering structure, as you can see on that graph on the right side. And we just introduced that intracavity ettalon. We call it thin ettalon. You will find out why in a second. And this gives us a coarse pre-selection of the resonator modes that are possible. So in gray, you would see the resonator modes. But since we look here at several tens of, it's 10 terahertz, so several tens of nanometers in this case. And there are so many gray modes that they really look like a gray big pattern in the back. And yes, just where the transmission of this pinkish line, this magenta line of the thin ettalon is very high, close to 1, only these modes would be supported. But still, this is not yet single mode. So what we do is we use a cascaded ettalon concept, which means we just add a different one, which has a way higher finesse, so thick ettalon, higher selectivity, and therefore we zoom into that graph a bit. Finally, only one of the resonator modes, now you can see these gray bars, each of them is one resonator mode, only one of them is really perfectly supported, and all the others will die out. So finally we end up here with a standard concept, a cascaded ettalon process, two-stage ettalon process, which gives us a single mode laser, and the achievable line width is typically in the range of less than 1 megahertz. I would say the commercialized systems that I've seen so far are typically below 500 kilohertz, or even below that one. One order of magnitude lower can be possible as well. So now we know about the single mode operation. But one major issue is the tuning. And one important feature of these tunable lasers, of course, is tuning. And yeah, you heard already before that one can tweak the temperature of the nonlinear medium, the nonlinear crystal, and do a wavelength selection by just heating or cooling that crystal, or even changing that crystal to a different structure. And this is what we call coarse tuning. If you want to do a more fine tuning, well, we introduce these ettalons in the cavity, and we can make use of it by just stepping those intracavity ettalons, moving those, and therefore we can achieve a picometer stepping. And last but not least, we have a third continuous tuning mode, which is truly continuous mode-hop-free scans by scanning the length of the cavity. So one of the 4 mirrors in that bow tie cavity, indicated here with the red arrow, is driven by a piezo, and therefore the length of the cavity can be adapted. So what does happen if we do these last two tuning mechanisms? We have here some examples, some measurements from lab. So on the left-hand side, I show you now the stepwise tuning. What we did is, maybe first the graph, on the x-axis you see time, and on the y-axis on the left side, the frequency in terahertz, or for those of you who are more familiar with wavelengths, on the right side, the wavelength. And we just stepped now the ettalon in different step sizes to show how you can really change the wavelength or the frequency of that laser by just using this element. And the step size can be down to something like 2 gigahertz. Here you see the smallest step down to the left, around 2 gigahertz in the infrared range. Often it is quite interesting to have a truly continuous scan, and this is also possible, as I mentioned before, the mode-hop-free tuning, by scanning the piezo of piezo mirror here. And here we end up, we have a center frequency, and we scan the piezo around that center frequency, and we see again a frequency, or on the right hand side wavelength plot over time, and more than 10 gigahertz in the infrared can be tuned. So now we have narrow line width, we have our tuning mechanism. Well, one thing that Jaro mentioned in the beginning is we want to have a wavelength coverage in the visible wavelength range. And if you listen carefully, you probably already found out that if we pump with a laser at 532 nanometers, which is quite common, even more common for OPO's 1064 nanometers. But let's go for this example, 532 nanometer pump laser. Well, it will produce signal and light photons around 1064 nanometers. And yeah, here we have a coverage, for example, from 900 till 1300 nanometers, but that's everything else than covering the visible wavelength range. Well, maybe the first attempt, one could think about just shifting the whole picture to the left by shifting the pump laser towards the UV. Well, I think the hardest issue there is the realization of finding a pump laser in the UV, which is high performance, single longitudinal mode, and having enough power and having a good lifetime. Definitely a tough challenge. But we can, instead of that, just have a second nonlinear optical process, the well-known frequency doubling or second harmonic generation, SHG. And well, we start from 900 to 1300 nanometers, and by frequency doubling, yeah, we end up with half of the numbers in wavelength, so 450 to 650 nanometers, which is perfectly covering the visible wavelength range that we wanted to achieve. So here's a short wrap up of the whole design of a commercialized system, and it might be a bit overwhelming, but we go through step by step, and you've seen already most of these parts. So on the left hand side, you see at first the pump beam going to the nonlinear medium, and then this singly resonant OPO cavity design, which is in this case resonant on the signal beam. We painted that in, yeah, I would depict it as orange, and outcouple in red color the idler beam. But by swapping this mirror, changing the coating of this mirror, we can just do vice versa. So keeping the idler and outcoupling the signal. And therefore we have access to the full range from 900 to 1300 nanometers in such a concept. We do see the two ettalons for mode selection. So let's call it wavelength fine selection with the two intra-cavity ettalons, and also the cavity length tuning with the piezo can help to have a really fine selection of the desired output wavelength. Then behind the first cavity, you see here we have the remaining pump laser output, and we have here a pick of mirror which goes to a reference cell, or as I wrote here, to a pound draw hole stabilization scheme. So we have an inbuilt reference scheme which helps us to keep all these actuators here under control. And finally, the output of the remaining pump and the signal or the idler, whoever you've chosen from with this mirror, are accessible as well. We were aiming for visible tunable output. So the new part is now the right-hand side cavity, which is again a resonant cavity for frequency doubling. Again, you need a nonlinear medium for that well-known process, and we have the resulting tunable output in the visible from 450 to 650 nanometers. So let's look at some key specifics or key performance parameters that you can achieve with such designs, just to give you an idea about the orders of magnitude. So commercialized systems nowadays can cover from 450 nanometers up to 3.5 micron in different models, and up to 260 nanometer gapless tuning range in the visible. And typical output powers in the visible range are more than half a watt. So several hundred milliwatts are easily possible. The line width should be less than 1 megahertz. That's what we hope for. And here you see a measurement of one of our commercial systems, which is well below 500 kilohertz as a typical line width in the visible range. And also in terms of frequency stability, we use our internal reference cavity for stabilization, and typically the laser without any other feedback can drift over hours like 150 megahertz. But if you require even higher frequency stability, you can do a closed loop feedback with a wave meter, and that's what is shown in the graph on the left side, and enhance the frequency stability down to the megahertz range over several hours by active feedback loop. So now, to wrap up this part, I want to show you a video about the motor pre-tuning, which I casted in our lab. Standard wavelength approach 460 nanometers, and you see on the upper left side the wave meter, which shows 919.97 nanometers, so the IR wavelength related to this. And in the middle to the left, this is the live graph of the wave meter in terahertz. What we want to do is we want to scan now the piezo of the OPO resonator to scan the frequency. And therefore we have this function. We can give a duration in milliseconds, a lower limit, an upper limit, and just run this command and see what happens to the frequency of the laser. So the measurement we see here live in the middle to the left. So you can do that on the GUI, or what I prefer is writing it here on this console. And I give a start command in a second. So just here we go ahead, and you see it immediately starts scanning now. Before it was just movements on a megahertz scale, and now we do here a motor-free scan on the gigahertz scale, so more than 10 gigahertz scan. I hope you can see the scale on the left side, otherwise you need to trust me. I see 871 as the upper and something like 657 as the lower edge of this scan. And of course, you can adapt this to your needs, these kind of scans. So by just giving that command that we showed before, let's say we slow it down to a 10-second scan. Mode is 1, which just means a triangular shape, and we restrict the range of scanning just to scan only a shorter frequency range. And you see on the right-hand side how easily it can be adapted. And of course, other shapes or scans can be performed in a similar way and coded as well. Yeah, with this, I would say we have all tools that we need for quantum applications. We have a widely tunable visible laser light source with narrow line width. And with that, I would like to hand over to my colleague, Dr. Niklas Wasem, who is the application specialist, telling you now about how to apply such OPO systems.
Yeah, thank you, Corbinian. So this is Nick, and I've got the honor to talk a little bit about application results with this laser. So most of the researchers using C-wave for quantum applications do photoluminescence excitation spectroscopy. I'm pretty sure that most of you are well familiar with this technique, but to those who aren't, let me give a quick introduction here. So the challenge can be with single quantum centers that it is not possible to measure the absorption directly. And the way around that is not to measure the absorption, but to measure the photoluminescence when you excite the sample at different wavelengths. So this is shown here in schematic. You shine a light at different wavelengths, and then with a bandpass filter and a single photon detector, you look at the emission spectrum. And so you tune the laser to different wavelengths, and then you just integrate. You integrate over the photoluminescence. And this, if you don't pump into a dark state, this gives you an idea of the absorption cross-section, which is a vital part for characterizing these quantum centers. So one example where this technology has been used is in the group of Rudolf Bartich at the University of Münster in Germany. He and his team tuned the C-wave to 50 different wavelengths between 540 and 590 nanometers, and then recorded the photoluminescence emission spectrum, which you can see here. So in the center, you see the zero phonon line, which gets larger towards this part of the spectrum. And then on the right-hand side, you can see the remaining laser beam, which couldn't be blocked with the filters. So this is a weak signal, but you can see it, and it of course goes off to the right side with a different excitation wavelength. And another interesting part, which the group wants to study, is on the left-hand side, the phonon sidebanks. So these are longitudinal optical phonons that are excited here. Now, if you do the photoluminescence excitation spectroscopy, so that means you integrate over the entire intensity in these two lines for different excitation wavelength, you end up with a curve which looks like this. And the purpose of this research was to find out if these phonon sidebands can be used for absorption, so if they mediate absorption. And since these two features look similar and are symmetric around the zero phonon line, the answer is yes. Another application done in the group of Alexander Kubanek and Fedor Jeleszko at the University of Ulm, also in Germany, is photoluminescence excitation spectra of silicon latency centers, ensembles of those in diamond. So as the group of Rudolf Martic, they use temperature tuning, so coarse tuning of the C wave to set it to wavelength over almost the entire visible range, and then measure the photoluminescence excitation spectrum. And they did it for two different excitation powers. So the lower curve, this is for 5 milliwatts, upper curve for 10 milliwatts. You can see that there's actually just one big feature, so absorption band with a maximum around 540 nanometer and a width of about 100 nanometers. And that by increasing the pump power, you also increase the photoluminescence. So this is not saturated and pretty much featureless. They also did the same for germanium vacancy centers in diamond, and saw and observed this structure here with a clear feature 602 nanometer, which is associated to the zero phonon line of the center. So this helped this group to find out more about the energy level structure of these two important defects in diamond. And now when we focus onto this germanium zero phonon line, it is also possible to look at only one germanium center at low temperatures, so to freeze out the inhomogeneous broadening and the phonons. And when you look at this, you can actually do fine tuning of the C wave, so this mode-hop-free scanning. Then you can actually see a very fine level structure, which refers to the fine structure, spin orbit coupling of the different levels in this germanium vacancy center. And another interesting thing this group found is that actually, if you only use the resonant laser beam, then these absorption lines disappear. The center goes to a dark state, and you can switch it back on with a gating laser. They used 532, also tested for 5 nanometer, and could switch this transition on and off rapidly. And maybe to do a little bit of marketing for other HÜBNER Photonics lasers at this point, we also developed recently modulatable laser diodes, which can be used for gating or for spin initialization or spin readout of NV centers or other centers, and are state-of-the-art technology. So if you're looking for something like this, please feel free to contact us. And with this side comment, I hand back over to Jaroslav for the summary.
Yeah, so thanks, Gabinian and Niklas. Before we finish, of course, we would like to wrap up with a takeaway on what OPO technology can offer advantages. So I would say from the product view, the product features, well, with the OPO concept, it's possible to offer benchtop turnkey devices with an unprecedented wavelength coverage, in particular, which in particular applies for the visible spectral range. We demonstrated looking at the applications, a nice fit to the common applications in color center research. I'm sorry, I'm missing my slide. Oh, now we go. I'm sorry. So again, let me repeat myself. So yeah, product features. We are able to offer benchtop turnkey devices with an unprecedented wavelength coverage. I think, as explained by Niklas, there is a very nice match of the key performance characteristics, such as line width and tuning options, to color center experiments in quantum research. And yeah, last not least, let me mention that we are flexible, or the design concept allows for quite customer-inspired flexibility when it comes to adjusting tuning ranges and tuning protocols. So I would like to close with the notion, please contact us if you maybe haven't seen exactly your experiment in mind. Please don't hesitate to contact us for discussion. Before closing, we would like to say thanks to the groups that gave us valuable product feedback and discussions. I'm sorry, I have issues moving the slides here. I'm sorry, everyone. Okay. So again, particular thanks to Rudolf Bracic and his group, the Nanophotonics group at University of Münster, Weibo Gao and his group from the Nanyang Technological University, Singapore, and Fedor Jelecko and his group, and Alexander Kubanek and his group from University Ulm. Just to mention some few additional researches if you want to dig further into some technological issues. So I think a wonderful reference for getting an overview on OPO technology is the monography Optical Parametric Oscillators by Ephraim Sadeh, which is actually free available on ResearchGate. If you want to have a closer look on the principle of quasi-phase matching and periodically posed crystals, there is a very nice supplier website. And recently a very nice overview on developments in diamond photonics has been given in a Nature Communications paper. So yeah, with this, I'm handing over to the question sections.
Perfect, thank you for that, and thank you for that fascinating presentation. So we will now look at the questions from the audience. There is still time to submit a question, so do enter them using the panel on your screen. So the first question that we've got is, are there any demands of widely tunable semiconductor diode lasers for using as pump lasers to generate single photon emission?
Okay. Yeah, I try to answer this question. To be honest, I'm not 100% sure I really understand it. So the first part, are there any demands of widely tunable semiconductor diode lasers for pumping? Pumping an OPO and with the desired output performance means for us that's one of the most critical thingies when we have to design a new OPO concept. We need narrow line width, very frequency stable lasers at high power levels. Typically, diode lasers are not really what we are looking for, but we use diode pumped solid state lasers because of the line width and the frequency stability and so on. So the properties of a diode laser is typically, well, in general, I would say limiting at least the output of the OPO. It will kind of work, but I mean, the input parameters of the pump laser are very important for the output parameters of the OPO. Having a tunable pump is something we really do for some commercialized systems as well. So we sometimes tune, for example, our 532 nanometer pump. You can also tune that one with a piezo a few gigahertz, and therefore the output of the OPO will follow. That's a different way of tuning. So such concepts are possible as well. I think the last part of it, how this relates to the single photon emitters, I don't get the question completely, to be honest.
Okay, that's brilliant. Thank you. So the next question is it possible with the system to do a really coarse scanning over hundreds of nanometers?
That's a clear yes. That's the temperature tuning or coarse tuning. And what we do, for example, when we do a factory acceptance test, we do that fully automized in either 1 nanometer or 5 nanometer steps. And we can just approach one wavelength after each other. And that is, yeah, there are some scripts available. There's a library available, so we can give all interfaces to implement your own experiments and tuning algorithms. And as Jaro mentioned on the last slide, the concept allows for customer-inspired adaptations of tuning ranges and protocols. And of course, we are quite flexible with supporting that.
Fantastic, thank you. So we have a small question here about the scalability of this technology. So is it possible to integrate this OPO into chip scale?
The answer is yes, it is. So there are research groups who are working on this. But it's always a question of performance that you get out. But in principle, yes, you can integrate this onto chip scale.
Great, thank you. So the next question I've got here is, how easily can the wavelength coverage be adapted or changed?
Maybe Corbinian?
Yeah, okay. Well, adapting the wavelength coverage involves several thingies. I would say the most complex is usually to find a suitable pump laser. So if you know which wavelength range you want to cover, you find material, nonlinear material, which is suitable for that range. And there are like materials like lithium niobate or lithium tantalate available, which have a broad wavelength range where they are transmissive. So that is not really the limiting factor for most of the wavelength range, I would say. But finding a good pump source is typically the most limiting or the hardest.
Great, thank you. So quite a detailed question here. What would happen if you use a 266 nm single frequency laser source at greater than 1000 MW with narrow line width and high reliability in case of stability and noise as the pump source? What is the response for signal and idler spectra?
So can you, I just don't see the question at the moment.
Okay, maybe I can just quickly repeat the question if I can find it. So if you use a 266 nanometer laser with a watt of output power, if that can be used as a pump source. In principle, I would say yes, but it really depends on the nonlinear crystals you can use. So most of the materials get pretty opaque at these wavelengths, and this will be a challenge. But if you have a tunable, if you use a crystal, that should work in principle.
Yeah, probably I would like to add, it's easier to go again for longer wavelength with a longer pump and then do a frequency doubling instead of going down to these wavelengths. But this is, as Niklas just said, a matter of available materials.
Fantastic, thank you very much. We've got someone that's asked a question here that says they're new to signal and idler, and could we clarify what we mean by it?
So maybe I answered. So this is just a naming. With the OPO technology, you always get two different wavelength output, which both together obey energy conservation. And the one that has got higher energy is always called signal, and the other one is called idler, which doesn't mean that it can't be used. This is just a wording. It's just a name.
Brilliant, thank you. I hope that helps. So we've got another one coming in here, lots of questions here. Is the CW OPO thermally stable? So how long can it operate without mode hopping?
Typically, it doesn't mode hop at all because we built these OPOs on chilled platforms. So under lab conditions, it doesn't mode hop for really a lot of hours. And I mean, as I showed, if you want to be really sure, you can have a feedback loop with the wave meter to stabilize on a mode. But mode hopping under constant conditions in the lab doesn't occur. It really depends on how the commercialized design is done, and of course you need to take care about thermal stability, but this is done in commercialized systems nowadays.
Great, and that leads me on to a next question actually. What are the biggest challenges in commercializing OPOs?
Yeah, I would again say finding the suitable pump laser sources, because many of the output properties of an OPO are depending on the input properties of the pump laser. And while we are quite lucky in this case, having a company which produces pump lasers at 532 nanometers with narrow line width and very frequency stable in a robust, shape. This is usually when we start to think about a design to adapt for a different wavelength range, the part where we have to look most that we find a suitable solution.
Fantastic. And we've probably got time for just a couple more. So we've got another one here. What are some of the most difficult limitations for integrating a pump source?
Well, despite size, of course, integrating is always relative. So we have a low power OPO, for example, where we really integrate our own Samba pump laser. Of course, usually the higher the power, the input power is, the larger the package of a laser is. And finally, it requires just some more space in addition to the OPO. Otherwise, integrating it as soon as the properties of that laser are good, it is mode matching and the incoming beam to our cavity, and that's it.
Thank you very much. And I'll just do one final question. What about the lab requirements and installation of C-wave OPO systems by HÜBNER Photonics?
So maybe I take this question. What you basically need is a regular wall plug, 240 milliwatts, 110. We provide a closed loop water chiller with the system. You need a computer with a LAN access, and then of course an optical table that is vibration isolated and floating, and a clear lab atmosphere, so ideally no dust, and stable temperature and humidity. So this is what can be found in most, if not all, labs that use or that look into these applications.
Great, and I think that's all we've got time for in terms of questions. Thank you to everyone in the audience who did ask a question. If your question wasn't addressed during this webinar, then you will be contacted with an answer at a later date. If you'd like to watch this webinar again or recommend it to a colleague, it will soon be available in the webinar section of the Physics World website. Thanks again to our speakers, our sponsor HÜBNER Photonics, and to everyone who's joined us today. This webinar is now over.